Well, hi, everybody. Welcome to N is for Networking. I am your co-host, Ethan Banks, along with Holly Netlitsky. And Holly and I pair up for mentor-style conversations about networking. And the goal is to demystify the jargon and obtuse concepts that come up in our world of packets. And hopefully, you come away with a better understanding of what's going on. So if you're studying for your first networking certification, you find yourself in sales or marketing at a networking company, or maybe you're a seasoned engineer and you just want to refresh network basics and maybe find an opportunity to tell me, well, actually, then this is your podcast. I love the well, actually comments we get sometimes where you tell me this or that I didn't mention, or maybe got a detail wrong. Send them. I love them. We're going to do future episodes with the well, actually kind of comments later and incorporate those in. They are much appreciated. Follow Holly and me on LinkedIn and the Packet Pushers community Slack group, which you can join for free at packetpushers.net/community. And today's topic, OSPF Basics. And really, this is the basics, the very basics. We're going to have some big ideas. We're going to talk about a few terms. And we're definitely going to get into more detail in future episodes, but we're going to keep the discussion to really just fundamental concepts today. And Holly, we've been waiting to do this episode for a while because we haven't gotten into any detail about routing protocols prior to this chat, have we?
No, I think we've alluded that we'd get there, and finally we have arrived.
Yes, finally we have arrived. And the reason for that, in my mind, in part, was as you and I were going back and forth, you were making the point, it's like, well, you had said something along the lines of in all your certification studies, and I know you've done a bunch of certs there in Juniper Land, you've learned how to configure things, but less about the concepts and the background why, and you wanted us to spend more time on that before we actually got into routing protocol specifics. I got that about right, yeah?
Yeah, exactly. I think that I wanted for us to take a step back from these routing protocols and, how do we do all this stuff, and just try and give anybody who's looking for, well, why do we do this, or where does it come from, or any of the questions you have before you even hear the acronym OSPF, just give some answers to that and really set the stage.
Okay. Well, all right. I'm sure you've done some coverage of OSPF in your cert studies. There's no way you could have escaped it with as many certs as you've got. So from your perspective, what is OSPF?
So OSPF, I mean, it stands for, maybe that's a good place to start, is open shortest path first. Sometimes I think I forget what all these acronyms stand for, so it's good to revise. And what it's really doing is, it's a routing protocol. It's a dynamic routing protocol. It is helping to learn which is the most optimal route to get from router A to router G through the path, and, at the least cost, so to speak.
Mm-hmm. Well, okay, so right, we're trying to forward a packet from a router's perspective. It needs to forward a packet from itself and then forward it out another interface to its ultimate destination through it, and it doesn't necessarily know what that path looks like, but it knows the next hop. That's the thing that we care about here. So when we say open shortest path first, there's a calculation that's being done by the routing protocol to determine the next hop away from me, that's going to get this packet towards its destination the fastest, or the fastest. That's a misleading term, but via the shortest, most efficient, optimal, there we go, path is via this interface. What do we mean when we say cost? We talk about shortest path first. We talk about shortest. I would define shortest as lowest cost.
Yes.
Because that's what OSPF cares about is cost as its metric. What do we mean by cost?
Well, so I think shortest is misleading, because we think shortest and we think distance, but that's not necessarily the case. But I think cost is really the fewest hops usually at a basic level, assuming that you haven't played with any metrics or you don't have any preferable paths along the way.
Well, it could mean hops, but from an OSPF perspective, it doesn't actually care about hops, because I would define a hop as number of routers you're going through.
Yeah.
So So cost in an OSPF sense is the cost of a link. A link between two routers is
Yep.
assigned a cost, some number. And it could be that it's a lower cost to go through three routers and a more expensive cost to go through a single router or a single hop. Well, why might that be?
Well, that comes down to the costs of those links. So that kind of comes back to shortest doesn't necessarily mean length, but it means, okay, if we've got three links and each is a cost of 3, you've got a total cost of 9, but you might have 4 links with a cost of 1 each, which is less, and that would be your least cost path, like 4 total cost versus 9, if that makes sense.
So we've been hinting all around it here, and from an OSPF perspective, cost is the magic number. What is cost based on? What is the actual underlying network characteristic that cost for a link is based on? It's not a trick question.
I'm like, what? The cost of a link? I mean, usually, I really don't want to put my foot in my mouth here, but like,
okay. I'm catching you early in the morning. It's speed, right?
Okay, I was gonna say that, but I was like, I don't want to say speed, and then it's not speed, but I'm pretty sure it's speed.
Right.
I'm thinking way too hard here.
Speed or bandwidth? You're really overthinking it. No, that's exactly right, and that's why you can have a router be a single hop away that has a higher cost than a path that might go 2 or 3 other routers that happen to have much higher bandwidth, more speed, and therefore lower cost links to get through. And you'd rather than go through that. Well, let's put some numbers to it. Is it if you've got a 1 gigabit link and a 10 gigabit link, you've got a 1 gigabit is only is 1 hop away, or you can go through 3 10 gigabit links, which is faster. The 3 10 gigabit links is going to be faster, right? Even though you got to go through multiple routers in our imaginary scenario here with the lower cost. And you described it exactly right earlier, where you said, if I've got a link cost of I forget what numbers you used. I'll make up new
3s
numbers.
and 1s.
So 3s and 1s. Okay. What if we've got a link of let's say our 1 gigabit link has a cost of 100, and my 10 gigabit links have a cost of 10, and I have to go through one hop to get to a particular destination. That's a cost of 100, but I got to go through 3 different links to get via the 10 gigabit path. That would only be a cost of 30, 10 plus 10 plus 10. Well, 100 is greater than 30, which is my lower cost route that path through the multiple 10 gigabit links versus the single 1 gigabit link. Wow, we really made that hard. I don't think we could have made that any more complicated for something that's pretty straightforward.
I've got these visuals in my head, and I wish that I could project them onto the screen so like it would be less complex, because I have it in my head. I just need everybody else to listen and hopefully see the same picture.
Oh, maybe we need to do screen sharing at some point, and try that for some of these. Those of you watching this are going, dude, just do it. I'm watching on YouTube. Do the screen share right now. Well, okay. We'll get there. But the thing is, we're like an audio podcast who's transitioning to video. And so as soon as we start introducing screen sharing, and it's like, what do we do about the audio people? So we got to figure that out at some point. But anyway, if you haven't noticed on YouTube, I'm starting to do more lab stuff. So maybe I'll do a lab exercise that kind of illustrates this if you're brandy new to OSPF. All right, so let's back up a second, Holly. We're gonna cram a 30-minute conversation into an hour again, aren't we? I can see that happening. That's what's happening.
It's looking like that.
Okay, so OSPF, open shortest path first. Shortest equals lowest cost, and links are assigned a cost. That cost is based on bandwidth, the bandwidth of the link. So what is a path then? And we've kind of just been talking about it. It's all the links that a packet traverses to get to whatever the IP destination is. And maybe there's 5 different ways that you could get from where you are to where that packet needs to go through some mesh of interconnected routers. Which in enterprise networks, it's usually you don't have some complicated mesh. You might in a service provider network, especially if it's like national and you're going through a bunch of cities where you have limited fiber paths, you might make that you're more likely to see a big mesh there. But in enterprises, it tends to be more straightforward, more point to point. You know, Holly, is that kind of your experience with customers?
It depends. We always say that. I need to find a different way to phrase that, but it does depend because some customers might use if they have multiple different locations, and I've seen this with a customer, each location has their own router and they're turning that into a mesh without necessarily a central hub. So it's not
so
obviously as complex, but like you've got 6 different sites and you put that into an OSPF area, and now all those 6 different sites can route in different ways depending on what that shortest or lowest cost path is between them. But it's never like really, really complex of like 20, 30 plus.
Could we describe those 6 different routers you were saying as like edge routers at the edge of their different locations?
Possibly.
Yeah, okay. But they, rather than a hub and spoke topology where you'd want everybody to come back to a central location and then bounce back out to wherever it's going, they'll build a mesh there. Yeah, and that certainly we see that in SD-WAN topologies. That's pretty common. Whether they're using OSPF to do the routing or not is a very different question. But the point being, OSPF can take a mesh environment like that and calculate a whole bunch of different paths through that and then come up with lowest cost. And it does that with something called Dijkstra's algorithm, which, as you and I were prepping for the show, you told me you know things about this that has actually nothing to do with networking, because Dijkstra is really math that has a broad set of applications that happens to show up in OSPF, but it's not like unique to OSPF.
No. And I might have mentioned this in previous episodes, but this specifically was a turning point in my excitement for networking, because if you've seen my background, I came through industrial engineering and then I did a master's in operations research. Pretty much the fundamentals of operations research are optimization algorithms. All routing protocols are optimization algorithms. How do we get from A to B in the most efficient or shortest way? And Dijkstra's algorithm is one of these operations research algorithms. Like, I studied this not in terms of routing protocols, in terms of, I think, planes flying somewhere between which airports, or cars traveling between destinations. And I've done this math both by hand, I've coded it. I loved it. I think that makes, like, I don't think everybody loves it, but when I came across this, I was like, wow, this actually makes so much sense to me. And I guess my master's is networking, like network routing protocols somehow.
Do you have enough memory from your work with Dijkstra's algorithm to explain roughly how it works?
Sure. I'll try and explain it in the simplest way I can. There are a couple key things, and one of the things is you think shortest path and, okay, well, I'm just going to take all the links that have the lowest cost and that must be the shortest path from A to X, right? But the thing is that's really key is you don't know that unless you've tested all of the other paths, right? There's no way to say that this is the shortest unless you know the state of all of those other links and all your options. So what Dijkstra's algorithm does is it's got all the nodes. Okay, let's treat routers as nodes. And I don't want to make this too complicated, but you've got multiple different nodes. And it's going to move from the starting node to the nodes that are then connected to that. Assess the costs of those links. Pick the shortest one. Move to that next node. Assess those links, and then go back to the other node to assess the links from the one that was a higher cost to make sure that it knows, okay, it might have been a higher cost, but maybe that first cost was high and the next cost from that node out was lower. So it's pretty much expanding from node to node to assess every single link and the cost associated with it from A to X. And by the end, not only have you assessed every single link between every single node, but you have tracked the optimal path along the way. So you're saying, okay, A to B is this, A to C is this, okay, this is the least cost. From C to D is this, but B to X is this. This is actually now the shortest cost. So you keeping track along the way of every single link. It gets very complex doing it by hand, but it's really important because the fundamental is you don't know it's the shortest path unless you've assessed every single path, right?
So one of the things that's implied there in that process is the more complex the network is, the more nodes, routers that would be present in the network, and the more links that are interconnecting them, the more difficult it, no, difficult's the right word, but the more time it's going to take for Dijkstra's algorithm to settle on what the lowest cost path is.
Yeah, because the computation gets more complex and there's more to assess.
And then what happens? So I know the answer to this one. Let's see if you do. What happens in OSPF when there is a state change? A node goes down or a link goes down.
So, well, I guess you don't really think about this in terms of Dijkstra's algorithm, but obviously you do in OSPF. But if a link goes down, you now need to let the other nodes know. Say, hey, I don't have these links anymore. You need to recalculate. Perhaps I was on the shortest path. I don't necessarily know that, but you need to recalculate and see what the new shortest path is without me being here.
And Dijkstra's got to run again. Yeah. I know there were ways back in the day. So let's do a little history here. I know with OSPF, let's talk 20, 30 years ago, when CPU on board of a router that would do these calculations they weren't that powerful. And so you had to be careful about how much you asked that router to do so that it wouldn't be maxed out and unable to do all the jobs it needed to do at any given time. Running Dijkstra's could be a big deal. And so there was a rule of thumb that said, I want to say no more than 50 routers in an area, something like that, because you would, every time there was a significant network change, an interface goes down, a node disappears, your router crashes, something like that, all the routers in that area would have to recalculate the current state of the network and recompute shortest path, run Dijkstra's again. And that could be really taxing on a CPU way back in the day. It's not such a big deal anymore, but it certainly was. That was the design consideration. And so I kind of remember, again, going way back in time, there was a rule of thumb of something like, I think it was 50 routers. If you do more than 50, you're probably pushing it. You need another area at that point. And we haven't even talked about OSPF areas yet in this conversation, but we do have a key point to bring up here, since we're talking about areas, and that is well, let's back up even further than what I was just about to say. OSPF as a routing domain is organized into areas, an area being a group of routers that are interconnected and are participating in the same look of the network, the same understanding of what the network is. That's terrible.
I would say, if you think of it as an algorithm, an area is all of the routers that know about each other and are participating in this open shortest path first calculation. That's an area.
The key being, all of them have to have the same database. They all see the network the same way. They all know about all the links in the area. They all know about all the nodes, the routers that are in the area. They all have the same link state database, LSDB, if we're talking an OSPF nomenclature. And so all the routers in an area will end up with the same link state database. They look and understand the network identically. They have to, or else you're not going to get a consistent forwarding behavior as a packet moves through that OSPF area. In modern day, we're recording this in 2025 here, you can have multiple areas still, and there are some reasons why you might want to do that, but you aren't driven by the reason of, oh gosh, we got to be careful not to overload the routers with too many Dijkstra's algorithm calculations that it's got to do. That's not really a deciding factor because we got lots more CPUs, much more compute horsepower that can handle that. So just curious, leaning into you who visits a lot of customers and many of them are running OSPF. Do you see typically single area OSPF deployments or multi-area OSPF deployments?
Single area, I don't think I've seen a multi-area yet, but what's interesting is I didn't know that, I don't want to say multi-area is frowned upon, but if you read the community Slack and it comes up, people have very strong opinions of running multi-area OSPF. So I think that's actually where I realized, I was like, oh, maybe this is not something that is a basic or fundamental, but when I was learning OSPF, it didn't mention this like discrepancy between, or maybe best practice, maybe that's the better word, between having a single area or a multi-area, and why I think we've moved towards single area OSPF possibly, or maybe it's just more of a personal preference. But that was never really discussed. I learned about OSPF in area 0 and area 1, and like, this is how we're going to connect them all, and why? I'm not sure. And I was never told that part. And
okay, so when you're reading opinions about why single versus multi-area, what are the opinions that what seems to be the zeitgeist out there? What's the general consensus from in your opinion?
I mean, I think the general consensus is like, why would you need multi-areas? You don't have any constraints on, like you mentioned, maybe back in the day, you could only have a certain amount of routers in a single area. Well, you don't have that constraint now. So I guess, what is the use case? And I think very seldomly do people have a real use case for having multi-area. And if you think about it, if you have multi-area, you now have multiple areas that are all going to have to run this algorithm, find their own shortest path, and then I guess share that if you want to share them between areas anyways. But like, what is the use case? And I'm yet to find someone who has given me a really solid, well, this is like rebuttal to somebody saying you don't need multi areas. No one really comes back and says, well, this is exactly why. It's like, okay.
No, I tend to agree with that. Why would you do multi-area? Generally speaking, you wouldn't. But there are some OSPF behaviors that need to be understood that I suppose could drive a network designer to go, we're going to do multi-area in this case. The key thing to keep in mind here is all the OSPF routers in an area will have an identical link state database, and that link state database includes the routers themselves and the links between them, and also the routes themselves, what destinations you're trying to get to. And so where this gets interesting is if you want to do something like, I want to filter this route out of my OSPF database. I don't want to see that route in my routing tables. You can't do that. Well, you can't do that easily. There are ways it gets tricky to do this, because if you filter, assuming all these OSPF area or routers are in the same area, if you filter a route from router A using whatever technique the vendor gives you to do that, that route's going to show up in the other routers in that area because you didn't filter the route at that router, so it is no longer being announced. Everybody's link state database has got to be identical, right? That's the only way we're going to get consistent forwarding behavior through the area. And so if you want to filter a route, suppress a route because reasons, security reasons, whatever your reasons are that you don't want that route to be in the routing table, you have to take the same action on every router in the routing in the area. You can't just suppress it on one router and go, good, I killed it on router A, so he's not going to announce it to router B, C, D, and whoever he's neighbored with. No, it's definitely going to be announced, and you're going to have to filter on all those other routers too. So that's one of those behaviors where it's like, how do I deal with that? And it can be kind of annoying and drive you nuts if you were expecting I'm going to filter this route and it's not going to show up on the other routers that are downstream from it because it's not going to be announced anymore. No, that's not how that works. That's not what's happening. All you're doing is on that single router actually filtering that one route from making it into the RIB and then the FIB, ultimately, the forwarding information base. Show IP route. It's not going to be in there. But again, from that one router, the routing protocol still knows about that route. Is that a use case that many people have? I mean, I can remember one time over the years where I had that, and I actually didn't quite understand this about OSPF behavior, where it's like, wait, I squashed it on that route. Why is it showing up downstream? Because OSPF, dummy. And I went, oh, okay. Other reasons that might be interesting here, you can't do things like summarize routes within an area. Do you know what I mean when I'm talking about summarization of routes?
Yes, I didn't realize you can't do that. I guess I never thought about doing it with OSPF.
You can't do it inside of an area, right? Like if everybody's in the same area and everybody's link state database has got to be the same. And it so happens I know about all the 192.168 various /24 routes I might have in my network, and I try to filter them or summarize them, not filter them, but summarize them to a single announcement of 192.168.0.0/16. You can't do that within an area. Do you know where you can do it within OSPF?
Between areas, I would assume.
Yeah, you can do it between areas. You can do some kind of summarization between areas where what the announcement that will be from one area into another area will just be that summarized announcement. Hey, everything that's in the 192.168 address space, we've got a bunch of /24s we've allocated to different sites. I'm just going to send one announcement from this area to everywhere else that's a /16 that incorporates all of those. So you can do it in between areas. You can't do it within an area because, again, the link state databases have to be identical. That's the way that's going to have to work. So is that a use case? I mean, why? Let's go back to history again. Why would you have done summarization to begin with? Is a question.
Yeah, it's a good question. Care to answer?
Go ahead, speculate. Tell me why you think you might have wanted to do that.
Well, I mean, if you think about it, if you've got, I don't know, however many IP addresses on that same route, it's much easier to, instead of specifying all these different IPs that perhaps are, I don't know, a couple hops away, you can just say, okay, I know that I can get to this subnet, for example, and the next router will get a little more specific along the way, instead of keeping every single possible route in your route table.
And I think, to me, that's one of the reasons as a network designer you would have done summarization. You would have been very careful about your address planning and so on. Okay, everybody that's coming across the WAN from here, I'm going to assign network address space out of this larger block, and I'm just going to announce the one larger block from the WAN into my core environment, let's say, something like that. Keep the routing table cleaner. Don't show me all of these extra entries in my routing table in my core. Let's keep the core routing table look simpler. So there's a couple things in play here. One is from an aesthetics point of view, from a troubleshooting point of view, you're making things perhaps a little bit easier on yourself if you can be that granular and then that particular and organized so that your outlying networks are summarized when they show up in your core network, assuming your network's been designed that way. It just makes looking at things, a bit easier. From a resource perspective, resource consumption, we talked in one of our episodes about TCAM, things in memory constructs that store forwarding entries so that you can do very fast forwarding lookups. I forget what episode number that was. We talked about that and high bandwidth memory and a few other tools and techniques that are related to the hardware and the chips that are down inside of a network forwarding device. TCAM used to be really limited, and so there was a concern of, well, how many entries can I actually fit into the TCAM that's available to me on a particular device? And if you were limited, one of the techniques you would use to reduce the amount of TCAM that was being consumed was summarization. So if you had a really, really big network and you were limited to, say just a few thousand, again, we're going way back in time here, but if you were really limited, you could get more out of that core routing device, let's say, by doing summarization. So instead of 10 different subnets, you could summarize them into maybe a single statement, a single routing entry that would cover that, and do, as you were describing before, this bigger route. You're going to forward in that direction, and then it's going to get to that router doing the summarization that knows the more specific routes, and then it'll fan it out to wherever all it needs to go. I think old school graybeard network designers would still like to do summarization where they can. It always made me feel happy when I could do summarization, even though in modern day, do you have limits like that where you're like so worried about the amount of TCAM or HBM that you've got available that it's like, I got to conserve it. I got to summarize so I've got enough space to fit everything in. Probably not. I mean, most networks are not going to. I mean, I worked on a network that was, complicated with 2,000 odd routers, and I was still only dealing with like between 5,000 and 6,000 routes in our core. It just wasn't that many for what the device was capable of handling, as opposed to, say, a data center network. Like, I mean, you're selling boxes, Holly, that I think can handle what, like 1 million different route forwarding entries, something like that.
Yeah, it's a lot.
Yeah, yeah, exactly. Yeah, the big iron these days they're expensive boxes, but the big iron can definitely do that stuff. And so if you have a data center that's got a bunch of even host routes like /32 IPv4, a host route where you're literally routing on the IP of the host, it's not even a network with hosts in it. You can really, fill your routing table full of as 1 million routes, maybe even more. I don't know. I know I've
it
seen
might
stuff
be
with 1
more.
million.
It's a lot.
Yeah.
They big numbers, which some
Yeah.
customers are concerned about. I mean, I've seen the numbers, I'm like, really? And then you see their
What are you
network, and
doing?
you're like,
Yeah, what
oh,
are you doing that you need all
really? Yeah.
that? Yeah, exactly. Okay, well, a few other comments about areas. We've talked about areas. Areas in OSPF have numbers assigned to them, and there is one very special area called the backbone area. What do you remember about the backbone area?
So that number-wise, that's area 0.
Yep.
And that's really the backbone.
Yeah.
That's the area that that is where every other area is connecting to, and usually how they communicate with area 2 to area 1 is going to go through the backbone.
Yes. Yeah. That's exactly right.
The hub, if you want to use other terminologies, but
yeah. No, if you're reading about OSPF design, they will use the term backbone. If we were to sit and draw it out, you'd see area 0 in the middle, and then whatever other areas are hanging off of area 0, and it's hub and spoke. Every other area looks like a spoke. In inter-area traffic flowing between areas. I need to go from area 1 to area 2. It's going to go through area 0. Now, it gets weird if you do things like, wow, I'm going to take a router that's in area 1 and a router that's in area 2, and I'm going to plug them together. And then they can talk area 1 to area 2 directly. Yeah, you can do that, and weird things start happening, and traffic doesn't flow quite like you think it does, because there's a reason that all traffic in an OSPF, in between OSPF areas, into area traffic is flowing through area 0. Do you know what that reason is? Why is OSPF like this?
not off the top of my head, actually.
The answer is loop prevention, but I don't have the details of that in my head because I went on a quest to figure out, like, why is this again? And I remember digging into reading it, and the answer is loop prevention, but I don't remember what it is about the math and the calculations that OSPF does in between areas that if you could just route willy-nilly between any area directly, you could run into loop situation. But I know that is the intent of all inter-area traffic having to get forced through the backbone area. It does have to do with loop prevention. And this is one of those esoteric things where when you study routing protocols and how they do their math, preventing a forwarding loop where traffic doesn't get to its destination. It just gets forwarded in a circle because something didn't converge correctly. You need to have the routing protocol prevent that in some way. Loop prevention is one of those core functions that prevent that. I know Daniel Dibb, he's a network engineer based out of Sweden, did an article within the last year, did some lab work explaining like, okay, so let's say you have area 1, 2, and of course our backbone area of 0, and plug them up into a triangle. So you got a router in area 0 talking to a router in area 1, talking to a router in area 2, talking to a router in area 0 again. How does traffic get forwarded in certain circumstances? And it ends up being this weird asymmetrical thing. So it's like, it's a thing you can do, but you don't want to do that. It's not the way OSPF was intended to forward traffic. Again, going back to this loop prevention. So the actual forwarding behavior is just strange, as I remember Daniel's post.
There's one thing that we haven't mentioned that I like just popped into my head, and it's really not in place of what you were saying, but it came up in my brain, and it's maybe to do, like, I don't know if it's relating to what you're talking about, but like the fact that OSPF is a specific type of routing protocol, that we define them by like an IGP protocol, like it's not gateway.
Interior gateway protocol.
Interior gateway protocol. There
yeah,
we go. And
yeah.
I think we haven't mentioned that. And I think that's important just to
it's a
mention
good point.
kind of what that means, and perhaps that's also kind of to do with why you don't connect areas.
There ends up being the use cases of where do you see OSPF applied typically, and so on, and then how you might see it deployed could factor in here. But OSPF is an interior gateway routing protocol. There's several other ones that are there. I think you would put ISIS in that class. You would certainly put Cisco's EIGRP in that class. A RIP, which I think we mentioned in the last episode, would fall into that. As opposed to exterior, an exterior routing protocol would be, what's the big one?
BGP.
BGP, yeah. So BGP, let's start with BGP to kind of give us a contrast. BGP organizes routers into autonomous systems, and rather than getting all the details of every individual route that might be within that autonomous system, you're announcing typically a summarized route and a path through autonomous systems to get there. You don't know every router along the way. You know every autonomous system along the way. You know, I'm going into this system. How it gets me into the system and out of the system to get me to my destination is its problem. And BGP usually relies on an interior, inside the autonomous system, if you will, gateway protocol like OSPF to do that forwarding. You don't have to do it that way. BGP blurs the lines these days between interior and exterior gateway protocol in the sense of how it is used.
And we'll get to that eventually.
Yeah, we will eventually. If you look at OSPF is very granular. You know, in the Link State database, it knows every router along the way, all the costs associated, and so on as it's making its forwarding decision. BGP doesn't make decisions about every router along the way. It doesn't know about every router along the way. If you look at one of the chief ways BGP decides best path, it's looking at a much higher level, the autonomous system, the AS path through BGP, Border Gateway Protocol. So interior gateway protocols are very granular, have all that detail. You see them underpinning BGP, perhaps, supporting BGP. You see them deployed in enterprises very commonly. You see them in service providers too. You see them everywhere, I guess, but they're playing a different role than what BGP does, or I should say what I would think of as an exterior gateway protocol versus an IGP interior gateway protocol. Okay, so we've talked about areas, we've talked about multi-area and kind of the distinction between multi and single area. We had these, why would you even do multi-area conversation. A few other things that we can note here. We're at 40 minutes. What is happening? It's so much more that we wrote. It's worth mentioning. Okay, so if you want to dig into some more basics of OSPF,
Mhm.
there's a good blog post you can read by Dante McNeil, who's a community member of packetpushers.net. By member, I just mean he's someone in the community. We don't have like a membership program or anything, but he wrote and published on packetpushers.net a blog post entitled OSPF Graphs, LSAs, and the LSDB, the Link State Database. So Link State Announcements and the Link State Database. Holly and I have been talking about LSDB, the Link State Database here, and LSAs, Link State announcements, or I'm sorry, I said announcements. Advertisements are what are exchanged between OSPF routers to populate the Link State database, and they have different types. And in Dante's post, he mentions the five most. There's more, but he mentions the five most common link state advertisements. For example, a Type 1 link state advertisement announces that this is a router. Type 2 is for networks, and and so on. And there's a variety of them. I just wanted to point out that article and packetpushers.net more broadly. I mean, if you want to dig into OSPF, so go to packetpushers.net, type in OSPF, and just find a whole bunch of podcasts that have been published over the years that cover OSPF on some level, and other blog articles that people have written, and so on. Great article by Dante, who contributed that to the community. We talked about. I can't believe we're at 40 minutes. Okay. So, dear listener, we're scrolling through the script trying to say what else to cover before we just call this for the day. I guess, Holly, we can talk about area border routers and autonomous system boundary routers. You want to hit those?
Yeah, let's hit them because it leads me into my area AS question.
Okay. Oh, another question Ethan's not going to be able to answer. Okay, let's see how we do. So when we talked about multi-area routers or multi-area OSPF design, and then a router that has an interface in, let's say, area 0 and a different area 1, that would be classified in the OSPF world as an area border router, an ABR. So if you're thinking about network design and you were like sketching on the whiteboard what your your OSPF network's going to look like, that router with interfaces in multiple areas is an ABR. It's an area border router. It matters because your area border router will need to run not just one but multiple Dijkstra algorithms, link state calculations, because now it's got to pay attention to multiple areas and multiple link state databases that it's keeping track of. Area border routers are also where you can do things like summarize routes between areas because you decided you wanted to do that, and so on. You're announcing between areas the different routes from different areas. So if your ABR it's going to have a leg in area 0, it will announce routes from area 0 into whatever the other areas are that it is connected to, and vice versa. That's its job. So that's an
Do you
ABR.
specify what routes it's going to advertise? Because you might not necessarily want everything in area 0 to be advertised into area 1.
You can do filtering
Yeah.
of some sort there. Yep, you definitely can. You can also, we haven't talked about area types. There's different types of areas, and you can do things like, I'm only going to announce a default route into this area because of the area type that it is. And again, that's something to talk about. Like we should talk about in a future episode, area types and link types as well. Or I should say OSPF network types for a particular link. Like there's point-to-point and point-to-multipoint and non-broadcast multi-access. There we go. I couldn't say it before when we were planning the show either. And so on. And all of those things are implementation details that are interesting and relevant. And some of them are historical. For instance, is there a use case in 2025 for the non-broadcast multi-access network type for OSPF? Maybe. I can't think of one off the top of my head, but maybe, because so often we're dealing with broadcast or point-to-point, and that's kind of what we normally see. There could be more. Anyway, so ABRs. I mentioned ABRs. Another one, autonomous system boundary router. This is not an area border router. It's not like another name for it. It's a different thing. Do you know what an autonomous system boundary router is, Holly?
So that's Not really in terms of OSPF, and I think this leads me into my question. Maybe describe what that is, and maybe it'll answer my. I guess let me give you my question. So in OSPF, right, we've got different areas. All of those areas, if I'm correct, are viewed as one autonomous system.
Yep.
Whereas, like BGP, you've got different autonomous systems. Do
Sure,
you
yep.
ever have multiple autonomous systems with like multi-area in, like you talking about an autonomous system boundary router, which I'm assuming routes between ASs, but do you see where I'm going?
I think so. So in BGP, autonomous system has a specific meaning. It's a specific context. You
Yes.
actually have an autonomous system that's got a number in
Yeah.
BGP routers that are members of that autonomous system as assigned by that number. And there are private autonomous systems, and there's a group of numbers that have been reserved for the use of private internal, as in not to be advertised on the internet. And then there are public autonomous system numbers that the internet uses because everyone's got to have their own unique autonomous system number that's been assigned to them. Rather than getting into the details of that, I'm more making the point that in BGP, an autonomous system and an autonomous system number has a very specific meaning, and it is part of how BGP computes its forwarding path from one place to another. That's not what we're talking about when we say autonomous system, as in autonomous system boundary router in OSPF. There is no concept of an autonomous system number that you assign to OSPF, but I think you categorized it exactly right when you said, I can have multiple OSPF areas. I can be running a multi-area OSPF network, and all of those together create a conceptually an autonomous system. Yeah, but does it mean autonomous system like we mean in BGP? No, it's not the same thing. It's a more of a mental construct.
Okay.
So I've got, maybe a different way to put it would be routing domain. I've got a gigantic, OSPF domain that's made up of a bunch of routers that could be single area, multiple area, whatever. It's my great big routing domain, my great big OSPF autonomous system, if you will. Maybe another way to think about it would be you can have multiple OSPF processes, each of which have their own unique link state databases. You can do something like that, and each of those different OSPF processes, and this does get into specific implementation details by vendor, as I recall. But I mean, if you kick off different router OSPF processes on a particular device with unique numbers assigned to them, you're creating distinct link state database domains, as I recall. Boy, that's going to be a little bit of lab work for me to remember exactly how that's implemented. My bigger point is we've got all of these OSPF routers, even if it's multi-area, create one gigantic autonomous system, which doesn't mean the same thing as autonomous system with BGP. Does that help? Nope.
The problem is, like, I'm going down a very, like, so you've got, okay, so then I guess let's get back to what you were talking about, this autonomous system boundary router.
Right.
If an autonomous system in terms of OSPF is not really an autonomous system in terms of BGP, well then how do I have an autonomous system boundary router if it's not like a defined autonomous system?
Well, let's back up a step. Maybe this will help. What does an ASBR do? What does an autonomous system boundary router in OSPF do? What's its job?
Yeah, that's a good question. It's announcing routes, I'm guessing, from somewhere outside of OSPF. I want to say into OSPF, but then would it be going into area 0 specifically? Like, does it matter where that router sits?
No.
Okay.
I mean,
because I guess all their link state databases are the same.
You can do it wherever you want.
Yeah.
You can put that ASBR wherever you like. It doesn't have to be area 0. You could have it if it's multi-area, you can have that ASBR sit in whatever area you want. From a design perspective, maybe you want it to be in area 0, but you don't have to do it that way. No.
Okay, so that's really going from OSPF internally to outside, let's say. Outside of that OSPF. I don't like using autonomous system. Yeah, let's say domain.
Call it a domain.
Thank you. Yeah, that I can't say
Yeah.
area, but
Yeah,
so
yeah.
it's okay. Then I get it.
Okay, so that's what
Mm-hmm.
that ASBR is doing. It's taking routes that originate from outside of OSPF, from outside of the OSPF system, if you will,
Mm-hmm.
and injecting them into OSPF, and vice versa. You can send routes out a different way, or outside of the OSPF domain into that other autonomous system, routing domain, if you will. And where you would commonly see this deployed would be, Cisco would call it route redistribution. You've got two networks you need to join together. The one network was running EIGRP as its interior gateway routing protocol. The other network was running OSPF as its interior gateway routing protocol. How do we get these two networks to exchange routes? Well, from the OSPF perspective, you're going to have a router that is going to be an ASBR, Autonomous System Boundary Router. It is going to be running OSPF and EIGRP, and you will configure that router to redistribute routes from EIGRP into OSPF. And the EIGRP routes that come from that routing domain into the OSPF domain will be announced as LSAs, type 5s, I think. Let's scroll back up.
Yes.
Yes. Yep. And there's type 4 summary LSAs if we're using summarization, and type 5s, external LSAs, Link State Advertisements coming from that other routing domain into OSPF. What do those look like to OSPF? They look like routes, like any other route. And if you're doing a show IP route, you'll see that they're a specific type. Oh, these were learned externally. These weren't originated from within my OSPF domain. They came from outside my OSPF domain as injected by the ASBR. You can also do mutual redistribution, which is, and if we continue our example, we're taking routes from the EIGRP domain, pumping them into OSPF, and then we're going to take routes from OSPF and announce them into EIGRP. And then you got to be really careful with routing loops that you don't get that wrong. There's a lot of, you can really blow things up awesome, hard, just amazingly if you get your redistribution scheme wrong. There's work you got to do to make sure that is done well, especially when you get into, gosh, I don't want that. What happens if that router dies? I don't want that my connection between the two networks to go away. I got to do it with two routers, and now you're doing mutual redistribution from two routers, and that's where the pain starts. Yeah, so that's a whole other discussion. But okay, now that we talked about what the ASBR is doing, do you feel better?
Yeah.
You just don't like autonomous system because of what it means to BGP.
Because in my brain, I'm like, oh, well, if it's in an autonomous system, it's got a number, and now maybe I'm doing like EBGP around, or like with OSPF inside it, and now, and I'm like, my brain just going down a path where I'm like, just because of the word. And I think often that happens in networking where we're like, oh, let's just call it this, and it's fundamentally, sure, mentally it's an autonomous system. I understand why we're using that terminology, but I think once you start learning BGP, I see autonomous system and I'm thinking that. And I actually went back to my notes, that like the little textbook I have, and I'm pretty sure, and let me find it. There's a diagram that has OSPF and the autonomous, it shows you the autonomous system around it. I'm like, this doesn't look good. This does not, like, why?
Well, it could be because in that context, it was truly a BGP autonomous system using OSPF underneath as its interior gateway routing protocol. That is very possible.
And it's got an AS, but it's got an AS number. And
right.
But this is my problem with training sometimes. At this point in this book, BGP was not a taught concept yet. So that shouldn't be there, in my opinion. Because now we're talking about ASBRs. I'm like, oh, cool.
Because you can
BGP.
definitely have an OSPF, Autonomous System Boundary Router, without BGP existing on your network in any way. That is exactly true. Is that a typical deployment? Is that where the person writing this book was probably thinking? I'm going to guess from the way you're describing this diagram, they are assuming OSPF is the IGP underpinning the broader BGP autonomous system. That's my guess.
And these build, obviously, like all trainings give you the diagram and then it'll teach you about the thing in the next thing, like the next step. And I get that. But I think, this conversation about this ASBR has really clarified things a lot, that because just because you see a term doesn't mean that you can assume that it's linked to everything else, is really what I'm getting at. And I apologize for the rant.
Brain, though. No, you have such an engineer brain. That's the way all of us think. It's like, wait, this says this and that means this, doesn't it? It doesn't? I'm confused. What's happening right now? Yeah, we all go through this thinking process. So you're just yeah, you got the engineer brain, Holly. That's just, it's who you are.
Yeah. Well, at least I've clarified it in my own head, and I hope that anybody listening can take value from my autonomous system rant and has clarified it for them as well.
Okay, we got to wrap this one up. So all you out there that are watching or listening, boy, oh boy, if Banks said something wrong and you need to do, well, actually, you can do that via packetpushers.net/follow-up. I will be honest, I've been doing OSPF for years, but I do forget some of the details and didn't look up everything that happened to come up in this episode because I wasn't expecting that. And so if I made some misstatement, please, don't be shy. Let me know, and we'll update in a future episode. And as Holly and I were talking, we definitely are going to have more OSPF conversations. There's lots more detail to fill out. I don't know that we'll do that in the very next episode or not. We'll see, because we've had some of you guys have come up with questions or comments that you want to make, and other requests for topics. Like somebody had a really interesting one. You want us to talk about troubleshooting, like a methodology for troubleshooting, which is there's no way that's an hour-long conversation. I don't know, Holly. Well, that's anyway. Packetpushers.net/follow-up for your well actuallys, or just anything you want to share, request for a topic that you want us to cover, and we'll add it to the list. Just so you know, we're like 6 weeks ahead as we record. So if you're like, I want to hear this, you're not going to hear it next week, because we don't record and then publish the same week. Holly and I travel, and so we have to have like this buffer of recordings so that we can handle our travel weeks. Please do all the things. We would appreciate it. Like, subscribe, leave a comment, tell your friends, all that stuff. We are everywhere that you find your podcasts, Spotify, Apple Podcasts, and anywhere else. We're on all the platforms, and including YouTube. And an increasing number of you are listening to podcasts via YouTube. And if you want to watch us talk, what we're publishing on YouTube these days is our talking heads. You can see us laugh and smile and make faces at each other while we're talking, and it's in glorious 1080p. And last but not least, just remember, networking isn't hard. Other people figured it out, so you can too.